evening. I hope all of you are doing well and ready, inshallah, for next week to come here to KVPM. I don't know. I'm guessing that some of you are already on campus, and I noticed yesterday. By the way, every day I give the classes from my office. So while I'm going out, I noticed that there are more students than usual. Usually, you will find maybe sometimes one student here or there over the past 10 months or so. But lately, I've seen a lot of students go and move and so on. So it's, honestly, I miss that feeling that to see students, let's say. So I'm eager to see you and meet you and you to see me. Unfortunately, you're going to see me in a situation where you're taking an exam, and I know that during an exam you're not really cheerful. And probably all of your faces are going to be kind of I don't know. So let's continue the class. By the way, inshallah, later today I will send you through WhatsApp or through a message or so, or an email or so, details about the exam. The exam will cover until the material, the last material that will be covered in the exam is today's class. Today we're not going to be talking about anything additional, more or less. Okay, so the material will only include the Fourier series. Okay, Akhwan? Anything that we discuss, the Fourier series until the point that we discuss today. Okay. In fact, until the calculation of the Fourier series, even some of the things that I'll talk about today are not included. Okay, Akhwan? So I'll give you clear, let's say, indication of. I'll give you a clear indication of where or what is the material that will be included in the exam, and details about the exam, what I will give you, what I expect from you, and so on. Inshallah, hopefully later today or tomorrow. Your exam is on Thursday, right? If I'm not mistaken. It's on Thursday, isn't it?
Yes.
Yes, yes.
Okay, yeah. So so we have about a week, and even if I don't send you the information today, maybe tomorrow or so, then the EE315, the other course, their exam is on Monday. So they only have about 4 or 5 days. So I need to maybe focus on them first, and then I'll inform you of details about your exam. But inshallah, things will be okay. So, you remember last class, I told you that, or what we did last class is, and I erased everything that we were working on. I told you that we will solve, or I will solve 2 problems. Now, this is probably similar to the example that I gave you, the one that we solved. I think maybe it may not be exactly the same, but very close. Okay? Maybe the numbers are slightly different here or there. Okay? And maybe the shape of the function is not exactly the same. But anyway, what I did is I went and solved it and gave complete explanation of how do you find the Fourier series. And as I mentioned last class, if I ask you to find the Fourier series coefficients, I expect you to solve until this point. Okay. Once you give me this point, you have completed the work for which is finding the Fourier series expansion. Okay. And what we did after that is we solved another problem, which is this, what we called the rectified cosine. And I think I explained to you yesterday the rectification. Rectification means you take the negative parts and flip them. Well, rectification comes in 2 different forms, in fact. And maybe it makes sense to talk about it here, because even the second example that I have is related to this. I added, so now you have 3 examples on finding the Fourier series. If I give you a sine, for example, or a cosine, this is the shape of the cosine. You have 2 modes of rectification. One mode of rectification, what you do is you remove the negative part and replace it with 0. So basically, this becomes the signal. Okay. This is called half-wave rectification, or you're passing the signal, the cosine, through a half-wave rectifier. Okay. So when you pass a signal through something that will remove the negative part, replace it with 0, this is called a half-wave rectifier. Another form of rectification is when you take the negative parts and you flip them up. So basically, you take the negative parts and replace them with positive, or basically you remove the negative or take the kind of the absolute value of the signal. So the signal becomes like this. Sorry, maybe I need to use a different color. Signal becomes like the following, black. Okay. Oh, sorry. and so on. Sorry, the graph is not accurate, but I hope that you understand the concept. This is what we call full wave rectification. Now, in this course, we're not talking in detail about half wave and full wave rectification, but you'll see that probably there will be several courses, including communication courses, including electronics courses, in which you're going to be talking about those. Okay, so I thought, since we're talking about it, it doesn't harm us if I just explain to you the difference between half wave rectification and full wave rectification. We saw yesterday how we can find the Fourier series of this. And let me just remind you, because at the end of last class, one of you, thank you so much, honestly I forgot the name, but one of you pointed out that I made a mistake. Okay, and the mistake was in, I'll show you basically what the mistake is. Okay, what we did to find the Fourier series here is we needed to find the period of that signal, and we said that the period is basically this much. It was equal to 6 seconds. How do I know that this is equal to the period? Because look, I can take 2 points in which the signal has the same phase. For example, it's at the peak value, or it's at the bottom value, or even you can take somewhere in the middle in here, but not in the middle here with the middle there. In the middle here while it's going up, and in the middle there while it's also going up. So all of those basically will indicate to you that this is the period. This is the period, and this is the period. Okay? So we found the period to be equal to 6. So the period of x of t is equal to 6. But the second thing that I wanted you to find, or that you needed to find in this problem, is what is the shape of x of t? If you notice in here, I didn't give you what x of t is. I just gave you a shape. And you cannot plug in a shape in an integration. You'll have to figure out what is that function is. Is it a cosine? Is it a sine? Is it a tan? Is it whatever it is? Okay? So to be able to find this, I told you that it is a full wave rectified cosine signal, which means let's find what is the cosine that generated this full wave rectified signal. And clearly the cosine that generated this is this. The blue line. Here is this. It's the blue line, not the red. The red is the x of t. The blue line, let me call it y of t. Now y of t has its own period, which is different from the period of x of t. In fact, we notice that t0 in here, t0 that we will use in the Fourier series, was equal to 1 over 6. I'm sorry, is equal to 6. Okay, which means that omega 0 will be equal to 2 pi divided by 6. Okay, but y of t has a different period. Why? Because when you take a cosine and you take the absolute value of it, negative parts flip upwards. So now you have a signal that has double the frequency. So clearly y of t here has a t, I'll call it tx, I think, or ty or whatever. Okay, ty will be equal to double the period of the tx. In fact, I cannot call it t0 because then you're confused. T0 above and ty there. Okay, so I'm calling it ty. Ty there will be equal to 12. How do I know that it is equal to 12? It's from here to here, or from there all the way to here, and so on. Okay, fine. So basically, the period in there is equal to 12. So now I need to find what is the frequency. It's a cosine. I need to figure out what is the frequency of that cosine. The frequency will be equal to 2 pi divided by 12, which is going to be equal to pi divided by 6, so I multiplied by 2. So this is the function that I will integrate. And then we said that let's integrate it from -3 to 3. But I could have taken the integration from 3 to 9. Or I could have taken the integration from 0 to 6. But we said that whenever you want to find, let's say, find the Fourier series, always find a good period to integrate over. A good amount of the 6 seconds. What do I mean by a good amount of 6 seconds? 6 seconds in which your integration will result in the least amount of work. What do I mean by the least amount of work? Meaning that your integration results only in a single integration. Yeah, basically your integration sometimes for some functions will turn out to be, or you'll have to divide it into 3 integrations or 4 integrations, like what we talked about in here. We had to divide the integration into different intervals. Here, 1, another one, a third one. So find a good interval, and we said that a good interval is this interval, from -3 to 3. If you take from 0 to 6, you'll have to integrate this which has a specific function, and you'll have to integrate this, which has a different function. Even if you take, for example, the interval from 3 to 9, that's in this interval, you'll only integrate a single function. But the problem is that this thing describes this. It does not describe this. Trust me, if you use this function and integrate here from 3 to 9, you'll get the wrong answer. And you know what the answer will be? It will be negative of the actual answer. Maybe I'll explain it to you later, okay? But anyway, if you needed to integrate this function, you cannot use this. In fact, you'll have to use a shifted version of it. Okay? Right? You'll have to use either a shifted version or put a minus sign in front of it. So you'll have to replace the t there by t minus, and the shift is equal to, I think, 6. T minus 6. This, if you wanted to use the other interval here, this interval, rather than the first interval, okay? You'll have to write it as t minus 6 and integrate this between 3 and 9. Okay? You got it, gentlemen? So anyway, so my mistake was, I think I had in the integration in here, I think, if I'm not mistaken, I think I had this also written as pi over 6. Yeah? Which is not right. It should have been pi over 3. Because this is T0, so this is omega 0. Okay? This is T0. This is, let's say, this is omega y, if you want to think about it, okay? Just like Ty, which is the period of the signal, the cosine itself, okay? This is its frequency. So they are different. Okay, Juan? So I just wanted to make sure that, to clarify this point, okay? Now, we did the integration yesterday, and we stopped at this point. If I'm not mistaken, I think this is where we stopped, okay? Now, I promised you that what I will do is I'll take this and plug it in MATLAB. Now, I had, you remember the tool that I used 2 or 3 classes ago? I could have sketched this, and it would give me almost the same thing. But that tool that I used was doing the opposite. I was sketching the signal, and it was giving me the answer. Let me show you that what we have got in here actually sketches this. Will actually sketch this, okay? So what I have is I have MATLAB open. I did it already last night. Also, I was very sleepy, so I was afraid that I'll make a mistake and I'll not get the answer. And it took me a while. Let me tell you exactly what happened. I plugged in one of the values incorrectly, and let me just open the code, MATLAB code. Okay, this is good. It's a short code. It's something like 4 or 5 statements. Now it is short. What made it longer is that I had it plot and so on, do some plotting. This is why it was long. But the actual code that will do the task is, if I remove this, plot in here. Hold on, let me see. This is the actual code. So it's about seven statements or so. And I could have even reduced it a little bit. Okay, so it's not very long. Sorry, you don't see the MATLAB. My apologies, because I was looking at my mobile. And none of you told me about this. Hold on, let me see. Next time, gentlemen, if I'm talking about something and you don't see what I'm talking about, let me know. So let me share with you. Go to Blackboard and start the sharing here, and share with you the full screen. Yeah. So this is basically the. Hold on, just give it a minute. I'm looking at my mobile phone right now. So. Okay. I don't see the MATLAB. I see Blackboard. You see MATLAB, or maybe I'm the only one who don't see MATLAB.
No, we don't see it.
No.
Just
let me stop. Yeah, hold on. Let me see. Okay. Share again. Share the entire screen. And let me open it. Now I think you see it, right?
Yes.
Okay. So the code that I wrote is, as I mentioned, about 7 or 8 statements or so. It's not very long, and if you know how to use MATLAB, this is basically the code. It could have been even something like 3 or 4 statements less if I compressed it, but I modified it because I wanted to plot. Okay, so I added some statements there for plotting, not more than that. Okay, let me just show you what happens if I run. Okay, yeah, all I want you to know in this, I don't expect you to know what I did in here is. Okay, I defined a variable which is called time from -9 to 9. If you notice, the plot that I sketched was from -9 to 9. And then I decided to go, let's say, plot an approximation for the signal for k between -100 to 100. Remember that k is the index. So basically, I'm using all of the coefficients from c -100 all the way to c 100, including the c0, which is the DC value. Right? And then define what is the value of the coefficient, each one of those coefficients in terms of k. So for each one of k, I'll get basically the value of the coefficient. And this is, trust me, this statement is exactly taken from here. From the solution of this problem. From this solution. Okay? This, I directly took it and plugged it there. I didn't do any modification to it. Okay? Initially, I plugged in here, instead of 12, I plugged in 10 by mistake. You see the 12 there, that is in the denominator there. I don't know, maybe I was in a hurry. I was too sleepy, honestly. I did, I think, at 11 a.m., sorry, 11 p.m. or so. I was too sleepy, so I, by mistake, plugged in 10. And I noticed that when I plotted, the plot had exactly the same shape that I was expecting, but the amplitude was modified, was not equal to 1, which is exactly what I have, the signal that I have in here. This, the magnitude or the height was equal to 1. It was 1.2, because instead of dividing by 12, I divided by 10. So it was a little bit higher. And then I struggled for maybe 20 minutes or so trying to figure out where the error is. And then I noticed that it was equal. It was because of that 12. Anyway, so I plugged this. And this is what happened. Okay, let me just run the MATLAB code. And I'll show you basically the plot, similar to the one that I have before. Okay. But this is honestly, Wallet, this is the code exactly as it is. I just got it from. Okay, I forgot, by the way, to mention this. And then I'm defining a signal x, and each time I'm getting x, adding the previous vector or the previous shape of x. Okay, I'm adding to it the coefficient, the ith coefficient, multiplied by the exponent. Remember that this was the form that we needed to represent the function. What we got from the Fourier series was just the coefficients. Again, let me just show you this in here. This is not x of t. This is not x of t. Okay? This is ck. Those are the coefficients. Then at the end, what you need to do is you need to write x of t to be equal to, for example, c0 multiplied by e to the power of j 0 times omega 0 t, okay? Plus c1 times e to the power of j 1 times omega 0 t, okay? Plus c2 multiplied by e to the power of j 2 times omega 0 t. يعني plug in طبعا the value of omega 0 and so on, okay? And طبعا I have to do it also on the other side, -1 and -2 and so on. Okay? So I got those coefficients, multiplied each one of them by a complex exponential, in which I took the t to be it has values from -9 all the way to 9, and then added all of those signals. Each one of those, think of it as a signal by itself. So I added 10 signals or 20 signals or 30 signals. I was adding the signals slowly, one by one. So initially, I was producing only C0. All of this, by the way, this becomes equal to 1 because e to the power of 0 is equal to 1. So I was generating only C0. Yeah? And then I was adding to C0, which is a constant. I was adding to it C1 multiplied by this, in addition to C of -1 multiplied by e to the power of -j 1 times omega 0 t. Okay? So I was producing this plot and displaying it. And then I was adding to it this plus the component that also exists there. And then I was adding the third in here and the third from there, and so on. And the reason why I was adding symmetric and always one component above 0 and one component below 0 is that both of those, the ones that are around 0, think of 0 as the one in the middle, the one C1 and C minus 1 combine together to give you the same thing. If you don't add both, you get a distorted signal. So each time to get a real signal that is symmetric, not symmetric, I mean a real signal, you have to add both C1 and C minus 1. And then add C minus 2, C2 in here, and C minus 2, and so on. This is basically what I'm doing. This is basically what the code is doing, without going into detail. I'm not going to ask you anything about MATLAB, by the way. Don't worry. Okay? And then I'm just doing the plot. Okay? So the loop there, each time, if you notice in here, I have a for loop. Each time it's adding two components. And this is how I'm adding the two components. I don't know if you notice in here. I'm adding to the value of x the ith component from one side and the ith component from the other side, without going into detail. Right? That's, I think, yeah, that's basically it. Okay. So let me run it now and let me show you. I think did I run it or not? Yeah. Okay. Break it and run it again. And let me just, for the sake of argument, let me tell you what I is, or I. Let me tell you what this quantity is. Without going into detail, let me say in here, let me just add title, so that we know how many items we have added. Let me run it now. Okay. Now this is the zeroth item. Let's say this is only C0. Okay. Now you don't have a title here because the title comes in the loop. This was plotted before the loop. Okay. Sorry, no, this is not the number that I want. I need to subtract 100. Sorry for that. I should have added it yesterday. I think I need to subtract 100. 101. Yeah. So now this is the plot. Yeah. As you see, it's just constant. By the way, this is the average value. And trust me, if you find the average of this rectified, full wave rectified signal, it will be for a signal, for a sinusoid or a cosine that is full wave rectified with an amplitude that is equal to 1, its average value will be 0.65 or 0.63. I don't know exactly the value, but this is exactly the average value. Now let me add one more component, and this is basically the other component added to it. Now notice this is a sine wave or cosine. In fact, this is a cosine because it's centered around 0. Okay, with a specific amplitude. The amplitude is about maybe 0.4 or something like this, 0.4, 0.5. Right? Add it to the DC, gives us this. Now, clearly, this is not the full wave rectified signal. Let me add more components. Now, I added a second component here. If you notice, this is 2. Add another one. This is a little bit distorted version of the cosine. Okay. Now I have 3 components, 4 components, 5 components, 6, 7, 8, 9, 10, 11. Notice that it's slowly. Okay. It is approaching. By the way, this is the 0 here. Okay. So you notice that until now, in here, I don't know if now I can zoom in here. By the way, I couldn't zoom in the tool, but notice in here, for example, if you zoom in, notice this is like a corner, and this is why the Fourier series is having difficulty in approximating this, or let's say in simulating this. But the more components you add, the more accurate this thing will be. Remember, now it's approximately 0.018. This point is approximately 0.018, and it's not sharp. Let me do more plots. It will become sharper and sharper. This. And trust me, there are small modifications that are happening to the signal, but you don't see them because now the signal is quite accurate. This is okay. Let me just finish until 100, I think. Okay. Oops. Try again. sorry, because I ran it twice. So let me just. My apologies for this. I'll stop just before 100 so that in case I ran it, maybe by mistake I ran 3 times or so. Okay, right? Now I've included 100 different components. Let's see how sharp is it at the bottom there. Remember, it was 0.018, I remember. Now look, it became significantly sharper. It in fact reached 0.0003 or something like this. So the more components you add, trust me, this will come closer and closer to 0. But trust me now that it's quite accurate. If you try, what did I do? If you try to plot, if you maybe I should have plotted the rectified cosine on top of it to show you that the difference between them is quite small now. Once you reach 100 components, they're almost the same. Okay? Right. So at least for the time being, let's stop this. Yeah. Now I went and solved another example. I'm not going to go over it. You have it in the notes. But this is what I did. I went and took, you see, the problem with this signal is that it's an even function. And if I show you, yeah, let me show you the C's, Control C. Okay. C is a vector that contains the coefficients. Okay. If you notice, those coefficients are real. I don't know if you can see them. All of them are real. Okay. How do you know that a number is real in MATLAB? If you have a number that is real, okay, for example 5, it will appear as 5 or 5.4, 5, 6, 5. This is how it looks like. However, if you represent a complex number, 5 plus 3 times 1i. This is, by the way, in MATLAB. If you have never used MATLAB, in the past, you could, okay, without going into detail, this is how you represent a complex number. Now, this is how complex numbers will appear. They have a real component plus an imaginary component. All of the values in here of C are real. And I'll tell you what the importance of this, or what does this mean in a few minutes, okay? But I wanted a situation in which the coefficients of C are not real. The C's themselves are not real. You know, they are either not even imaginary. I want them to be complex. Trust me on this. If your signal is even function, if you have an even function like this one, you'll always get the C's to be real. If the function is odd, like a sine, then the C's will always be imaginary, not complex, but imaginary. For you to have coefficients that are neither imaginary nor real, but complex, you must have a signal that is not even and not odd. Okay? And I'll remind you of something that we talked about before that basically illustrates this for you. Okay? So what did I do? I went and tried to find the Fourier series of this. In fact, by the way, I'll admit, initially I found the original problem was to find the Fourier series of this, which is called the half wave rectified signal. It's so if you have this signal, the blue signal, gentlemen, is what we call the half wave. Here, it's called the half wave rectified signal. Okay, and I solved the whole problem based on this, but it turned out that I also made another mistake. And when I plotted the Fourier series, and as I'll show you, it turned out to be the Fourier series of this signal. So again, this was the first signal that I did, that I just showed you. This was at about 11. This signal was at about 11:30 or so, or maybe 11:45 p.m. And I was too sleepy. So honestly, I did not want to figure out what the error was. Okay? I figured it out early today in the morning, and I didn't have time to modify it, to modify all of the solutions. So I just went and modified the signal itself. Okay, and basically I adjusted the problem based on the solution that I had. So what I did in here is, again, I found what is the period, and the period in here is from here to there, okay? Which happens to be equal to 8. And I also found what is the function in here. And the function was equal to cosine. It's a shifted cosine. Yeah? This basically was the function x of t. And then I went and did almost exactly the same process. The mistake that I made that gave me this is instead of the integration here being from, you see, the difference between this signal and the original signal that I wanted to solve, which is this, is that in this signal integrate from -1 to 3. Yeah? The integration over one period is the integration from -1 to 3. By mistake, I don't know why I put the integration there from -1 to 1 and did all of the solution based on this. And then I thought, you know, at the end, well, if I'm going to change now all of the integrations, I'll have to change a lot of things in here. And I didn't have the time, so I just left. I modified the problem basically to have the signal go from -1 only to 1. Okay? And basically, this is the solution that I got. Yeah? And I think I just simplified it in here. Okay, I'll talk about the simplification of this later. Okay? But this is basically the solution that I had. And I went and plugged it in MATLAB. And when I plugged it in MATLAB, it gave me an error. Not an error, but it gave me the following. Trust me on this. If I, in fact, I have the MATLAB code. Let me close this. And let me open. It's called the half rectified signal. This is it, yes. Okay. This is the, I'll tell you, if I remove the C in here and plug in the C, you notice that there are two lines on top. Okay. This is exactly, this formula is exactly the formula that we have here, which is this. Okay. But this is what happens if you run the code. And I'll tell you what the problem is. Let me show you. In fact, I think what happened last night, although I was too sleepy, but what happened last night was appropriate because I wanted to talk about this in the next couple of classes. So I thought, no, this is the time to talk about it. Let me just show you what happens if I run the code. Now this is the DC constant, the constant, which is 0.2 or something like this. Now after the second component, everything disappeared. Okay, and nothing appeared there. So when I tried to investigate, let me just show you. I came into MATLAB in here and just type what is C. No, not this. Hold on. See, I was expecting something different. Here. I think, hold on, let me see. Was there? Anyway, I'll tell you what happened. What happened is this. When I plugged in at a value that is k is equal to 1, if you plug in k to be equal to 1 in here, what happens? You get in the denominator there. You see, if you plug in k to be equal to 1 in here, in the exponent, there's no problem. E to the power of pi over 4 minus pi over 4 is e to the power of 0. So this turns out to be equal to 1. This will also be, I think, equal to 1, I think, or maybe this is not going to be equal to 1, but anyway, yeah, whatever is up, there's no problem with it. But when you plug in k to be equal to 1 in here, you end up with pi divided by 4 minus pi divided by 4, which is equal to 0. Yeah? So the denominator there turns out to be equal to 0. And you know that whenever you divide by 0, you get infinity. Now, in this situation, you don't get infinity, in fact. What you will get is, you see that the numerator there will turn out to be equal to 0 itself. So we get 0 over 0. And when you do this in MATLAB, this is what will happen. Let me just write, for example, if I write in here 1 divided by 0, MATLAB will tell you that it's infinity. INF there stands for infinity. But what happens if you write 0 divided by 0? It gives you a value that is called NaN. NaN stands for not a number. Basically, the difference between infinity and not a number, infinity, MATLAB knows that the value is very high. it could be very high or very low, either plus infinity or minus infinity. But whenever you have 0 over 0 or also infinity over infinity, MATLAB will tell you that this is not a number. This is an undetermined number. You know that if you have 0 over 0 or infinity over infinity, this number is undetermined. To be able to find this number, you have to do something else. Okay, Juan? So I needed to figure this out when I was very sleepy last night. Okay? But I did it. Okay? And this is basically what I did. I said, let me do the following. I took this formula, and maybe you're not going to understand this clearly now, but I took this and opened it. I just went and, not opened it, but I played with it a little bit, okay? I took this part, you see the 16 in here, I took J2 from it, and I took out 8 out of it. And I split it into 2 parts. And I took the J2 and put it under this. And the same thing I did from here. I split this into J2. And there is a reason why I'm mentioning this, by the way. There is a reason why I'm mentioning it. And you'll see that what I'm doing here, you'll experience in many courses in the future, in this course as well as many courses in the future. So I also split this into J2 and 8. And I took the J2 and put it under this. Now, does this seem familiar to you? This part and this part? Does it seem familiar? Have you seen something similar to it? Maybe with something under it. Father Abdurrahman.
It's just sine and cosine. I mean,
exactly.
In this case, it's sine. Yeah.
Absolutely. Thank you so much, Abdurrahman. You're absolutely right. Okay. Remember this formula in here. Okay? The Euler's formula. We said that it allows you to write a cosine in terms of complex exponentials, which means that if you have complex exponentials in this form, you can convert them back to a cosine. Now, what's the difference between a cosine and a sine? They are almost the same, except that in the case of a sine, you have a minus sign in there. Yeah, the exponents are exactly the same. If I wanted to write a sine, I'll have exactly the same, e to the power of j pi divided by 4, t minus 1, minus e to the power of minus j pi divided by 4, t minus 1. This exponent has to be exactly the same as this exponent, but with a minus sign. Okay? But at the denominator, you have j2 in the case of a sine. In the case of a cosine, you have 2. In the case of a sine, you have j2. Okay? So this is equal to sine pi over 4 t minus 1. Okay? And this is exactly what I noticed in there. That this exponent is exactly the same as this exponent, but with a minus sign in front of it. And I wrote it intentionally when I was doing the derivation, and I knew that something like this will happen. So I was doing the derivations there, putting in mind that I wanted this to be exactly put in the form in which there is a minus sign. And I could have taken the minus sign inside and changed this to positive. But then it doesn't become very clear. So I made sure that the minus sign is written outside. Okay? And the same thing happens in here. This is exactly the same as this, but with a minus sign in front of it. The only thing that is missing to get it, to converting it into a sign is I need to have J2. And I have J16 outside, so I kind of extracted or pulled away from it J2. So I put a J2 in here and put a J2 in there. Okay? And this is basically what I end up with in here. This is the second formula. This is basically that. Okay? And this is this. And what remains outside is only 8 now. Okay? And then I notice that this thing means this becomes a sign, and this becomes another sign. Notice that there's a kind of minus. They're not the same sign. One of them has a minus in here, and one of them doesn't have the minus. Okay? Now, how does this help me? You know, it's like a simple simplification. But in fact, once you notice that this becomes a sign and this becomes a sign, now you can do a significant simplification that will remove the problem of having 0 divided by 0. And here, as I mentioned, what this will turn out to become 0 over 0 at a specific value. Okay? What is that value? It's the value that k is equal to 1. This turns out to be equal to 0 over 0. Now, once you notice that this becomes equal to a sign, and let me now show you something else. I'm sure that this is the first time that you see this. Okay? we have in here sine of something divided by the same thing in here, if you notice. And also sine of something in here divided by the same thing in there. Forget about the 8. The 8 is outside. I can take it as, it's just a constant outside. Okay? All of this is just a constant outside. And the same thing here. All of this is a constant outside. But in here, I wrote it in there as a constant multiplied by sine of something divided by the same thing. Sine of something divided by the same thing. Whenever you have sine of x divided by x, there's a name for it. Yeah? Anybody knows this? Anybody has seen this before? I'm almost sure
Yes.
you haven't seen it.
Yes.
Have you seen it?
Yes, in Math 101.
Oh, okay. Well, I'm really surprised that you studied this. Okay. What is it called?
I don't remember what it is called, but
Okay.
the limit approaches, it approaches 1.
Exactly. Okay. You have seen it. Okay. Good that you mentioned this. You have seen it. Tfadal, Saleh. You have maybe a name for it?
Isn't it sync fix?
Sync. Yes, absolutely. This is called the sync function. Okay. In fact, different books will define it differently. This is called the sync function. Thank you so much, Saleh, and thank you. Thank you for both of you for telling me this. But when you studied this, you studied it for the limits. But this is a very well-known function. Yeah, this is a very well-known function that appears a lot in communication, control, and so on. It's called the sync function, and the sync function, sync, it's basically sin with a c. Yeah, the sync function of x is usually defined differently from one book to the other. Okay, it's usually defined as sine pi x divided by pi x. Okay, so to go from here to there, you have to insert that pi. Now, honestly, I looked at 2 books. I don't remember which one is yours. I looked at 2 books yesterday. In one of the books, it was defining it this way, and in the other book, it was defining it as sine x is equal to sine x divided by x. Okay, honestly, I'm not sure. I need to check. Okay, but anyway, most books will define it this way: that sync of x is equal to sine pi x divided by pi x. Okay, which means that we can convert now those 2. If you notice in here, I can take pi outside, or there's pi in every one of the terms in here. Okay? So I can write all of this as sync 1/4. Notice that I removed the pi. 1/4 minus k 1/4. And the same thing in there. Sync 1/4 minus k 1/4. Now MATLAB understands that the sync, you see, sync is sine x over x, right? Or sine pi x over pi x or whatever. Yeah? If you plug in the following, sine of 0 divided by 0. What does MATLAB tell you? It tells you that it's not a number, right? Or sine pi 0, let's say 0 times pi divided by 0 times pi. MATLAB doesn't understand that this is, it doesn't find the limit for you. It tells you that this is not a number, because it evaluated the sine 0 pi, it found it to be equal to 0. And it evaluated the denominator, it found it also to be 0. 0 by 0, MATLAB will tell you that I don't know how much this is. It's going to be 0. But tell it, I want you to find sync of 0. What does it tell you? It's equal to 1. Although, look, sync of 0 is exactly like sine 0 pi multiplied by 0 pi. I'm sorry, divided by 0 pi. So once I did this, honestly, last night it happened. I don't know. Maybe I need to. I don't know why it didn't happen to me today. But last night when I did, I think maybe I modified the function or so. Modified this function. Last night when I tried this, I noticed that when it stopped showing me the figures. In fact, let me do it, and I think it will probably produce to me values of C that are all not numbers. Just let me try it. Okay, let me just. What I'm doing is I'm just executing the whole code I think that eventually, yeah, all of the numbers will be not a number. Just give me a minute. Okay, let me see. See, I don't know what I don't know what I did. Honestly, I was too sleepy yesterday. Maybe I modified it or so. Okay, but when I did it yesterday, it told me that using this form, it couldn't evaluate it. But using this form, and if you notice that the second form in there uses exactly the same formula. There's the sink. And when I plugged in the sink, or I mean, when I put the sink in the function there, let me just show you the graph. Yeah, this is the DC value. Now this is the first, second component, third, fourth, and so on. Look, as I add, let me just make it a little bit larger. As I added more components, it's approximating the same signal that I was trying to find this Fourier series. Okay. So this is basically the concept. Now, those are, I don't know, I don't have the title in there, so I don't know how many I have added, but you understand, this is the concept, okay? So you notice that I was able to find the Fourier series expansion for 2 or 3 signals, okay? And trust me, if you do it properly, you should be able to find the Fourier series expansion for any signal, any periodic signal. Okay, Juan? So we've talked about the sink, we've talked about finding the Fourier series. Okay, now, there is a reason why I decided to. Do you have any questions, gentlemen? Anybody has any question or comment?
Yes, Doctor. Sin pi over 4, over pi over 4 shouldn't be sink pi over 4.
Sine. Say it again. Sine.
Sine.
Pi.
Yes,
pi over 4.
Over.
So like this.
Yes.
Over pi over 4.
Yes. Shouldn't be
right?
sink pi over 4.
It's from the definition. As I mentioned, there are some books that will call this sink pi over 4, okay? But some books think of it this way, that the sink, sorry, should be sink. Some books, or some books, if you open them and look at the definition of the sink function, the sink is defined as, the pi is internal in it. If I say sink 1 over 4, okay, this is equal to sine pi over 4. The sink, as if it is inside of it, there's a pi. Okay, this is why probably in the math, since you mentioned that you studied this, or you had talked about this in the math course, maybe in the math the sine, or let's say sink of 1 over 4 is equal to sine 1 over 4 over 1 over 4, or sink pi over 4 is equal to sine pi over 4 over pi over 4. But as I mentioned, some books define it slightly differently. They define the sink of x to include the sine pi x over pi x. Anyway, this is just a technicality. I mean, honestly, as I mentioned yesterday, I was looking at 2 books. I don't remember. I saw the 2 definitions in the 2 books. I don't remember which definition was in your book. Okay, so inshallah, I'll verify it, and I will base the answer here based on the one that is in your book. Okay, I don't remember. It was late at night, and I was too sleepy. Yeah. So I don't know if I answered your question or not, but basically this is the concept. Some books will insert the pi. The sink has a pi internal into it. Okay.
Okay, thank you.
Okay, sure. Now, the reason why I put this example is I wanted to talk, and I have about 10 minutes, which is, I think, enough to at least to illustrate or to start talking about this. Now, if I go to MATLAB, as I mentioned, I have intentionally, let me go to MATLAB. I have intentionally put a signal there that is not even and not odd, so that if you notice that the C's now, okay, are all complex numbers. Notice that this is one of the C's. All of this is, by the way, a single C. I don't know what value the C is, but it's one, maybe C of 85 or 75 or whatever. Okay, this is another C. So don't think of this as 2 individual C's. Both of those, one real component and one imaginary component. Okay? Both of those represent a single Fourier series coefficient. And if you notice now, all of them are complex. Right? Now, we can define two quantities. One of them is called the magnitude spectrum, or we can define two terms. One of them is called the magnitude spectrum, and the other one is called the phase spectrum. Magnitude spectrum and phase spectrum. Okay, I'll talk about the meaning of spectrum in a few minutes, probably. Maybe not this class, maybe next class. Okay, but whenever you have the C's for any periodic signal, then you can sketch what we call the magnitude spectrum of that signal, and you can sketch the phase spectrum. Now, you can do it manually, by hand, by doing the calculations, or I can use MATLAB. Since I already have the C's in MATLAB, okay, let me use MATLAB. Okay. What is the magnitude spectrum? The magnitude spectrum is nothing but the absolute value of the C's. If you take the magnitude, what is the magnitude? The magnitude of any vector is the length of that vector. And any complex number has a magnitude. It has a length. Remember that. Let me go back. Sorry, I'm switching a lot between MATLAB and, okay? If I tell you any vector, if I give you any vector in there, I can always represent that vector as real component, say real, and imaginary component. Okay? Or I can represent it as in polar form. This is the rectangular representation. Basically, this vector, let's say x is equal to A plus JB. If you represent it this way, this is rectangular form, just like what MATLAB was showing us. But if you want, you can also represent the same vector x. Let me put a line there to indicate that it's a vector in polar form, where it becomes equal to r multiplied by e to the power of j theta. Or we can write it as r with an angle of theta. R is simply equal to square root. R is equal to square root of a squared plus b squared. Okay? And theta is equal to tan inverse of b over a. Without the j, b over a. Okay? Now, if you plot the r, which is the magnitude for all of the different C's, and you plot the phase for the different C's, the r will give you what we call the magnitude spectrum. And the theta will give you what we call the phase spectrum. Now, the magnitude spectrum usually is more important. Let me plot for you the magnitude spectrum and the phase spectrum and show you. Those are different from the signal itself. In fact, the signal will have a specific shape. The magnitude spectrum and the phase spectrum are completely different shapes. Let me come to MATLAB and just say R is equal to, how do you get the magnitude? Absolute value. The absolute value of C will give you, basically MATLAB will go to each one of those C's and find its magnitude. It's let's say the length of the vector. If you think of each one of those as a vector, the R in there will be the length of each one of those vectors. Okay? And let me call it T is equal to, let me hold on. Angle, I think. There are angle. Let me just see. Okay, angle. Yeah. Angle of C. I think this will do it. Yeah, okay, yeah. But angle of C. Now, the phase in there, MATLAB will, if you write angle of C, okay, it's basically giving you the angle, the theta of it, okay? But fine, okay, I think it's okay now. Right? Let me write in here plot R and show you what. I'm sorry, I didn't do it properly. Close. This is not what I wanted. What I wanted is the following. R. One of the functions in MATLAB is called plot, which plots for us x versus y. Yeah? Another function is called stem. The difference between the plot and the stem is this. Again, I'm not going to ask you anything about how do you plot or how do you do anything in MATLAB. Okay? This is just for your information, just in case you're interested. What's the difference between plot and stem? If you plot, for example, those points, okay, MATLAB will connect them with straight lines. In fact, it's not going to connect them even with curved lines. Okay, so it will do something like this. In fact, usually if you have some points and you look at the plot in MATLAB, it's يعني the MATLAB will connect for you those points with straight lines, something like this. If you say stem, it will do this for you. It will put lines like that. Well, assume that they are separated equally. It will show you something like this. Typically, the magnitude spectrum and phase spectrums are plotted using the stem function, not using the plot. Okay. So initially I used the plot, but let me now do it using the stem. Stem. Yeah. This is basically the stem. Okay. Now, what does this represent? I'll tell you something now. You may not understand it very well. Yeah. But I want you to understand that the element there, the highest element, this is, let me say it this way. This is what we call the spectrum of a signal. What do we mean by the spectrum of a signal? The spectrum of a signal, gentlemen, and please try to understand me here, and I promise you that I'll explain it more. If I told you plot the signal X, this is the plot of X. Where is it? Okay. This is the plot of X. What is the X-axis when I ask you to plot X? What is the X-axis? It's time, isn't it? Okay. This thing shows you something like, it's not exactly, but it shows you something like the plot of the signal where the X-axis is not time, but it is, anybody knows what? Frequency. Okay. So this is something like the plot of the signal where the X-axis is frequency. If the X-axis is frequency, this means that this plot tells me, unfortunately, I cannot write in here. So let me just use print screen and come here and plot it. And this is probably the last thing that I'm going to mention. Come here and basically explain to you what this spectrum means. This, think of it as frequency in here. Frequency. And I didn't plot it properly. This should have been 0 in there, and this should have been 100, and this should have been minus 100. But unfortunately, the numbers there start from 0 all the way to 200. Okay? But the highest point there indicates to you how much energy, think of it this way, how much of the signal is contained at 0 frequency. The next one is how much of the signal has a frequency which is equal to omega 0, which is the fundamental frequency. Okay? Or remember the frequency omega 0? Okay? Basically, this tells you how much of the signal is contained at that frequency. The next one is how much of that signal is contained at 2 times that frequency. The next one is how much of that signal is contained at 3 times that frequency, and so on. And from that plot, it is clear that most of the energy or most of the content of the signal exists at 0 frequency. As the frequency increases, what happens to the signal? At the content of that signal, the content of that signal drops. And in fact, even if I continue further, you'll see it drop continuously until eventually at infinity it will become equal to 0. Okay? But basically, this gives us an indication of, is that signal, does it contain low frequencies a lot, or does it contain high frequencies a lot? In fact, I'll just mention this and I'll stop. If the signal that I had in, where is it? In here. If the signal was not like this, and clearly this signal contains mostly low frequencies. The high frequency components of that signal are not that much. If the signal was something like this, in here, high frequency, and maybe I'll solve another problem like this. Okay? If the signal was a very high frequency cosine, you'll see that the sketch of the magnitude spectrum would be completely different. You might find that there's no DC in here, or at 0 frequency, the stem will give you small dots in there, but once you reach a specific frequency there, the stem will start to increase like that, and maybe drop after that. Inshallah, I promise you that I'll solve another problem like this. What does this plot tell you? It tells you that the signal that you are plotting in here has a lot of components at a specific frequency there, and no components, or basically the content of that signal at low frequency is 0. Maybe the content at high frequency is also 0. But the content at a specific frequency, for example, which is equal to 1 megahertz or 1 kilohertz or whatever, is a lot. Okay? So basically what the magnitude spectrum tells us is, it tells us what are the frequency contents of the signal. Right. I'll stop at this point. Inshallah, I'll meet you on Sunday. Until Sunday, as I mentioned, what I will do is, there will be no quizzes, by the way, next week. It's only the midterm exam. Okay, fine? So I will not give you a quiz. Only the midterm exam, which will be on Thursday, and I'll give you, inshallah, enough details about the midterm exam. Inshallah, if not today, I promise you maximum by tomorrow. Okay? So if you have any questions, please ask. If you don't have any questions, I'll see you, inshallah, Sunday. Yeah.
Doctor, did you put the solution for the quiz 2 on the?
No, until now, I haven't included the solution. I included part of the solution, but I haven't uploaded the solution in the lecture note that I have in here is significantly updated compared to the previous lecture note. In fact, I even solved yesterday or the day before. I solved one problem on convolution, okay, because I thought that only one problem is not enough. So I went and solved another problem and solved 2 or 3 problems on Fourier series. So inshallah, probably today, tomorrow, inshallah, I'll put the I'll upload the lecture note, which will contain the solution. I only included, I think, so far 2 parts of the solution, 2 of the 3 questions of the solution. So inshallah, tomorrow, before I upload the updated lecture note, you'll have even the 3rd part of the solution included there. Okay?
Okay, thank you.
Sure. Who else has raised his hand?
أنا عبد
If you have
الرحمن.
raised your hand, عبد الرحمن تفضل.
دكتور، لازلت ذكرنا قبل يمكن 4 كلاسات ناقشنا فكرة الأورثوغوناليتي ساين، أورثوغوناليتي كوساين، بس لازلت مش فاهم إيش علاقته بالموضوعنا يعني، أو يعني إيش السيجنيفيكانس حقه.
طيب. Okay. أنا شرحت هنا also in the updated version of the lecture notes. Okay. شرحت somewhere. I think. I remember. Okay. شرحت بس I wanted to add some figures but I didn't. Okay. Inshallah, I promise you that I will maybe explain it. Maybe I'll even add a little bit explanation to it. Make sure that it is, hopefully it is clear. Read it once I upload the lecture note, hopefully by tomorrow or so. And if you still do not understand it, let me know, and I'll be happy to maybe connect with you at night or so and explain it to you. Well, let me say it this way, Abdurrahman. The concept of orthogonality of vectors is not really important for you to solve using the Fourier series. I didn't want to go and just talk about Fourier series without giving you kind of background on where did Fourier series concept come from. In theory, if you wanted to solve a problem that is asking you about Fourier series, you can solve it without knowing what is the Fourier series, because it's just something that is mechanical. You just plug in, find the period, find the omega 0, find the period of integration, and plug it in that integration, and that's it. Okay? It's just that I'd like you to know at least the basics. What is the idea of the Fourier series before you go and work on it? So inshallah, I promise you, I'll make sure that this appears to be clear, and I'll upload it, read it. If you still cannot understand it, let me know, and I'll be happy to explain it to you. Okay, Abdurrahman?
Okay, thank you very much. Okay.
Sure.
Take
Faisal? حياك الله.
Doctor, can we know where to end from the Fourier series for the midterm material exam?
I will let you know, inshallah, later today. I will let you know exactly what هذا الماتيريال الأخير اللي تكلمت عنها اللي هي the spectrum. Okay, this is not included. Okay, yeah. وطبعا all of my discussion about MATLAB and so on, this is also not included. I'm not going to ask you to sketch the Fourier series. Okay? It's quite difficult to find the Fourier series coefficients. So once you find the Fourier series coefficients, that's more than enough. And this is basically the last part of the material that will be included in the exam. But inshallah, I'll give you exact information about the, let's say, details about the exam later today, as I mentioned, or tomorrow. I promise you. Sure, no problem. Any other quick question, gentlemen? Okay, have a good day.